the Wi-Fi here. All right. How are we? Okay, fine. So we're going to go over some of the correlation things we looked at so far, a little bit more over linear regression, and introduce the new thing, which is multiple regression. Not difficult at all, but it's important that we look at it. Okay, so first of all, your assignment, as you know, is due Tuesday, I believe. That's right? Tuesday? Wednesday? Okay, Wednesday. Do Friday. Wednesday, okay. Wednesday it is. So, some points. As I covered last time, if some of the cell sizes in the chi-square are less than 5, which violates the assumptions of chi-square, do it anyway, because I didn't teach you Fisher's exact test, so do it as if it's a chi-square. You won't be penalized for it. For number 4, linear regression question, the goodness of fit I'm asking for is the R squared. We'll talk a little bit about that today. And when you're assessing the quality of the R squared, just tell me if it's good or poor. And today you'll find out what that delineation is, good versus poor. Okay, now people are asking about rounding and things like that. Some people round to 2 digits, some to 1. There's a lot of leeway in the answers. So the TA has been instructed with all the possible correct answers depending upon how you do it, because his job's cut out for him. Okay. Any questions so far about the assignment? Pretty straightforward. Yeah? All right. So we're going to review ranked correlation, which is Spearman's row, and we're going to review a little bit of unranked correlation, which is Pearson's row. One of them is parametric, the other is not. Do you remember which is which? No. Yay! Someone shouts things out like that. Spearman's is non-parametric, and the reason for that is it doesn't require a certain distribution in the general population. That's what parametric really means. So when do we use ranked correlation, i.e. Spearman's, when one of the variables, at least one of the variables, is ordinal? Now, if just one is, we prefer to use tau, but I didn't tell you how to do tau. But when both are ordinal, we definitely use Spearman's. Okay, and we like to do it with their extreme outliers, for example. That gets rid of the effect of outliers. And when the ranges are dramatically different, it's really useful as well to switch over to a ranked methodology. How do we do a ranked correlation? If you remember this, you've got to rank the data. Well, we'll go through another example. Even though you're doing it already for an assignment, we'll do it again. And we do the computational procedure as I taught you in class. The trick, because it's so obvious, it's elementary math, the trick here is deciding how to rank it. And that's the qualitative, subjective human component that people sometimes mess up. And depending upon how you rank, that'll determine if it's a positive or a negative correlation. And I'll show you what that means in a second. And here's that second example. So the example here is there a correlation between how long an inmate spends in prison and their attitude while they're in prison? So the assumption is that if you have a good attitude, you'll probably spend less time in prison, you'll get out with early release. If you have a bad attitude, you probably break some rules in the prison and you'll stay there longer. So we're going to measure a time in prison in months, and attitude is a psychiatric scale from 0 to 100, where some psychiatrist has assessed these individual and says 100 is fantastic attitude and 0 is a crappy attitude. Right, so here's our data. Obviously it's fake data. 4 guys with as much cultural diversity as I could manage: Bob, Frank, Raul, and Dan. So our attitude scale, so Dan's got crappy attitude, Raul's got excellent attitude, and these guys have something in between, and this is how long they spent in prison. Could I do an unranked correlation with these data? Why or why not? Your exam's going to be rough if you really don't know at this point. Could I do an unranked correlation? A Pearson's row? Yes. Why could I? Exactly. Now, you could argue that the range here are slightly different. So this range is 0 to 100, and this one is going to be, well, 0 to infinity, really. We spend a lifetime in prison. But in general, yeah, you could do an unranked correlation here, right? And you would get that number here, a minus sign. So in fact, the more time you spend in prison, the better your attitude, the less time you spend in prison, which makes sense, right? So it's minus. It's very highly correlated. It looks like this. So better your attitude, less time spent in prison. That makes perfect sense, right? Now, let's do ranked version. So here's the data again, same data. We're going to rank it. Who's got the best attitude? Well, he said it's Raul. Who's got the worst attitude? Dan. So they're 1, 2, 3, 4. Now look what just happened here. The highest number is the lowest number rank. Even though number 1 rank is the highest, it's the lowest numerical number. The computer or the formula doesn't recognize what you mean by first or second. It recognizes that 2 is greater than 1. So do you start sensing what's going to happen here in a second when we actually do the math? Let's rank the prison time. Who spent the longest time in prison? Well, Dan did, right? Oh, sorry, the less time in prison, it's Raul, and so forth, right? So depending upon how I phrase the question, the ranking is going to change. Is my rank the longest time in prison is the first, or the shortest time in prison is the first? Right, so that's the subjective human component, is how the direction I'm going to rank. I do the math, I get the difference in ranks, right? I square them, I sum it all up, I plug it into my equation, and I get, we did this already, our Spearman correlation of 0.8. Now the computer gave us minus 0.8. Here, it's positive 0.8 because my ranking here is such that the best attitude is ranked 1 and the lowest time in prison is ranked number 1. Do you get that nuance there? So you may find this in one of your data analysis questions where the directionality is important depending upon the phraseology of the question. Curious. The computer blindly just ranks the highest number is 1. So the computer would say, this guy here, time in prison would be number 1 as the highest number. Doesn't realize that the shortest time in prison is in fact the best outcome. That's the difference. Okay. The lesson, how you rank it is important, depending upon positive versus negative. Okay, we can do significance testing for correlation. We did this already, and we're testing the null hypothesis of rho being 0. Now, in practice, that's not particularly useful, to be honest. For sure I'm recording. Am I recording? Please say I'm recording. Yes, I am. Good. In practice, that's not very useful because so it's different from 0, big deal. What we care about is it different from some other kind of number. When we look at correlations, we care about the actual size of the number, not so much if it's different from 0. But be aware that we can compute it. So we just computed rho equals 0.8. Does that mean we automatically reject the null? No. We have to go through this entire process. We look up a critical value in the back of the book, and we see that our rho is less than the critical rho, therefore we fail to reject the null. Isn't that bizarre? That despite the fact that we have a very high correlation of 0.8, we fail to reject the null. Statistically, it's the same as 0. The reason for that is the very low sample size. 5 individuals. So it's actually not a very useful thing to test whether or not rho is statistically different from 0, but we do it anyway to show you that it's possible. In practice, we tend not to do it. All right, cool. There it is. So SPSS would have done it already. They found a p-value of 0.2. 0.2 is very high. The p is not low. It's not lower than 0.05, so the null does not go. But again, we tend not to look at that. We look at the number only. So now let's look at linear regression. Because there is this relationship between Pearson's correlation and linear regression. Remember that the way we write linear regression, or a straight line equation, is different from the way you were taught in high school. In high school, it equals y equals mx plus b. Here it's y equals alpha plus beta x. The alpha, or a, as a textbook calls it, is the y-intercept. That would have been the b in high school. And the b, or the beta, is the slope. That would have been the m in high school. Okay? So once we fit a line, we have that equation. And we all know how to interpret that. The important part here is y prime is the predicted value of x. And we call the slope the regression coefficient. And the reason for that, as you'll see in a second, when we go to the multiple regression side of things, it stops being a slope, because we're on multiple dimensions now. It becomes a strange philosophical construct that we simply call a coefficient because we don't know what else to call it. Okay, let's do a quick little example again. Same data before. Our inmates, we're trying to see if we can predict how long they will stay in prison based upon their attitudinal scores. So why is this important? Well, if we can construct a straight line equation from these data, then we can apply that to other prisoners coming in the next cycle, let's say. So if certainly, I don't know, pick a name, Larry, Larry goes to jail, and we give him a psychiatric assessment, and he scores a certain number. Now we can predict how long he's going to stay in jail based upon these data. So we want time in prison equals alpha plus beta times the attitude score, right? And there's our line again. Okay, is this slope positive or negative? Well, it's negative. So it's going to be y prime equals a minus bx. We know that already. So as we've seen before, we compute the sums, we compute the averages, we fill in the blanks for these particular constructs, right? We've done this already. Then we multiply it out, and we have all these data. Then we compute our b. According to this formula, we get that number. We compute our a by plugging in that number into this formula, we get that, and we get that as our final equation. Obviously, I'm not going through the details step by step because we've done this already. But the important part here is that we are now predicting the time in prison. Now, does that have units? Does that equation have units? What do you think? The answer is yes. These are real-life examples. That's why it's important that each of the data points in our table have the same units. Here, attitude scale is in whatever, attitude points. The important part is time in prison is in months. So this is a prediction of your time in prison in months because our data is also in months. Okay, do you remember the difference, what we call the difference between the predicted number and the actual number? Yes? I'm sorry? Residuals is correct. Now, do you remember the symbol we used to write down? Epsilon is correct. Absolutely. That's important now. So units, of course, there's in months. And I always confuse the dependent and independent variables. But here, obviously, the independent one is going to be this, and the dependent one is that. Why? Because that's the way we've done it. In real life, we can reverse it. We could have written a straight line equation that predicts attitude score based on time in prison. But we've done this kind of fitting such that if I plug in the attitude score, which is independent to be what it wants, this depends on it. Now, the reason I ask this question is when we go to the multiple level now, as you see in a second, it matters what's dependent and what's independent, because we're going to see a whole bunch of different independent variables being modeled against one dependent variable. Okay, so once I write SPSS, I get that, right? I get my constant, which is my y-intercept, is 63.8, which is like 64, and the coefficient for regression is minus 0.665, which is like minus 0.67. So SPSS agrees with the math we just did, which is great. Okay, so if you want to predict how many years a person will be in prison if they score, let's say Larry scores 43 on his attitude test, we just plug in that number in here and we get 35.2 months. So that's how long he's going to spend in prison with his bad attitude. So how good is the line? In your data analysis assignment, I'm asking for a goodness of fit. That's what we're asking. How good is the line in terms of does it fit well with the data? Because as we discussed earlier, we could have drawn any number of lines, but our least squares method gives us a particular line. How good is it? We can do lots of things. We can do a significance test to see if the slope equals 0. We did that last time. And we computed our b over our root of n, I think it was. That gave us our t value. We looked at the back of the book. Or we can do specialized goodness of fit statistics. And that's what the pros tend to do, goodness of fit measurements. We're going to do just one goodness of fit, and that's the r squared. But we've just seen the r squared, or the r at least. Which one do you think this is, Spearman or Pearson? Whisper, 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 whisper. Any ideas? Well, I'll tell you, it's Pearson. Spearman is a specialized kind of ranked correlation coefficient, where now we're back to regular old numbers again. So that R is the same R we would have computed in a regular non-ranked correlation. So there is this deep relationship between correlation and linear regression, in particular unranked correlation and linear regression. Okay? So, as we mentioned, the errors are the residuals, and we compute that by figuring out from our existing data what the independent variable would have given us. That's our y prime. We subtract that, that's our residual, and we square it. We add it all up, and we plug it into this equation here to get, come on, I'm gonna fast forward to get 0.72. So we can go backwards and compute from the straight line equation our Pearson's correlation, 0.72. Okay, now that's r squared. To get r, I just have a square root of it. So r is just going to be the square root of that, 0.85. Right, still with me? We remember from several weeks ago how to interpret the qualities of r. We use this chart here. So here we had a 0.85 r. That means there's a high correlation. That's not a measurement of goodness of fit, though. What we like to do is look at r squared. By the way, what's r squared tell us? Do you remember? Yes? How much variation in one variable is caused by the other, more or less. Okay? And here's the cutoff. It's about 0.6, and this is relevant for your assignment. So if it's 0.6 or over, then we say it's a good fit, r squared, not r. If it's not, we say it's poor or bad. And r squared, of course, is the amount of variation in one variable that the other one is responsible for. Right? So I didn't go through step by step, obviously, because I assume at this point you can go through the equations yourself. But again, you fit the straight line equation, you extract from that r squared, and you determine, is that good or bad? Now let's say we wanted to use straight line equations to predict a student's GPA based upon 1 mark in a class. So a student has English class, they've got this mark, and we want to say that looking forward in the future, what their final GPA is going to be. Okay, so we're going to make this equation here. GPA equals some constant plus a correlation coefficient multiplied by their English mark. Right? That's easy. But what if there's several criteria? Because your GPA is not based just on your English mark. It's based upon a whole bunch of things. Obviously, it's based upon your marks from other classes too, but also it's based upon things you've done throughout the year, like how many days sick you were, and I don't know, how happy you were during the year, and maybe how many hours you worked your part-time job. Not how to compute your GPA, but how to predict your GPA. That's what we're saying here. It's a bit different. Okay, so there are all kinds of different variables that go into this. So in other words, you can have your GPA equals your English mark, your physics mark, your calculus mark, plus any number of things going down the road. This is no longer a straight line equation, but it is a linear equation. Do you remember why it's a linear equation? Even though it's not a straight line? Yeah? There's no exponents, exactly. And the exponents are over here, around these betas or b's. Now individually, that would be a straight line, and this and that would be a straight line, and that would be a straight line, but together they're not. There's something else. Can you visualize what that might look like? Probably can't. Probably nobody can. If there are probably 2 of these, you might be able to visualize it, but not 3, or not 4. Okay, this is multiple regression. It's several linear regressions combined into one, and it's on a multi-dimensional plane, so you can't really visualize it. You can't even graph it. This is what it would look like with 3 dimensions. That's as close as we can get. It's a plane. Anything more than that, it gets more complicated. That's why we tend not to try to even to do it. Okay? No one does it by hand, so we're not going to bother even trying. I have computers for that. In this class, we're not even going into how to compute it. But I want you to know when you would use it and what some of the parameters mean and how to interpret them. So this is an example of multivariate or multivariable statistics. The sticklers disagree on which term we use, multivariate or multivariable. I come from the multivariable tradition, which means if you've got many variables, it's multivariables. But if you got like several variables on one side of the equation, it's multivariate. Don't worry about it. Either one's fine. Okay. Textbook uses multivariate. So it's a class of stats in which you've got at least 3 variables going on. It's not just GPA and English mark, GPA English plus physics mark. Or if it was your time in prison, it's not just your time in prison and your attitude score, it's your time in prison, your attitude score, and which type of penitentiary you're in. Or maybe your income level or your race or your age, all these other factors. Because in real life, predictions aren't just based on one thing. They're based on a variety of different factors. So suddenly you can start to see how powerful this technique can be. Right? I mentioned earlier that we did an experiment with a former student in this class. I had her look at predicting who would win The Biggest Loser. And we use multiple regression to do this. We decided we're going to try to model, based upon previous seasons of the show, the final outcome variable, which is the weight, the final weight of the contestants, based upon several other variables. The initial weight of the contestant, their gender, their SES, their BMI, etc. And we found we were able to actually determine who wins the show. I was hoping to use that information for betting purposes, but there's a caveat in the show that allows people to vote each other off. So predicting who loses the most weight is actually not a useful thing to predict who wins the show. So you can't really bet. Anyway, one very widely used multivariate method is multiple regression. There are other ones. There's logistic regression, other kinds of regressions. This is just one of them. And in fact, your n-way ANOVA is a kind of multivariate method as well. We already touched upon that. So multiple regression is a type or an extension of linear regression. Linear regression is a type of multiple regression. So in the grand universe of regressions, multiple describes all the types of regressions in which the outcome is a continuous variable. Like how much time you spent in prison, like your GPA, like your height, like your weight, continuous variables. Anytime you've got more than one predictive variable, it's a multiple regression. So this is a powerful tool for understanding how these things interact to describe an outcome. So that's the final equation you're looking at. Y prime equals 1 intercept. Again, at this point, it's not even a y-intercept because there are multiple axes here. Each one of these things represents an axis. They're k-axes, so it's multidimensional. You can't visualize it. And each of these is a coefficient, a regression coefficient. That's why we don't use the word slope anymore. It's not a slope. You can't visualize a slope anymore. These are just coefficients. You might want to think about them as weights. So let's say this is time spent in prison. And this is your attitude score. That's how much money you made, and that's your race, or something like that. So each of these represents a weight. Maybe that's a huge number. So your attitude counts for a lot. How much money you made counts for a little. Your race maybe counts for a lot. And it's a way to sort of gauge which factors are most important in predicting certain outcomes. Really powerful technique. One of my grad students is using it right now to predict the health of women in an Indian slum based on BMI. And she's looking at about 20 different variables and weighting them. And we're finding out that their social rank counts more than their age or their SES. Fascinating stuff, right? So we solve for A and B using the same least squares criterion, but now it's in multiple dimensions. Obviously, you can't do this by hand. It's way too complicated, right? So we still try to minimize our residuals. That's still the technique here. And, well, worry about that. So here's an example here. So we have the time spent in prison, but now we've got height added on there. So we have attitude scale, time in prison, and height. How do we predict a model now to predict your time in prison based upon 2 variables, attitude and height? Well, we'll let SPSS do it. And SPSS says that your coefficient for attitude is minus 0.99, and for height, it's minus 1. So this is the new equation. Time in prison equals this constant, that used to be your intercept, minus that slope or regression coefficient times attitude minus that regression coefficient times height. Notice, if we just looked at this and ignored the height, these numbers are different from what they were before. Before it was 0.64 and minus 0.67, I think, right? Now it's that. Why are they different? They're different because this new bit of information has changed the game. It's not simply a matter of taking the original relationship and slapping on something. This has been folded into the relationship and has changed exactly how much the weighting matters. This is what makes this such a powerful technique. This is a linear relationship, and that's a linear relationship. And together, they're a multiple linear relationship. As I mentioned, that's not the same numbers as they were before. It's changed. So, with the linear regression, the simpler linear regression, we had this thing called R with a small r. That was equivalent to the Pearson correlation coefficient. For multiple regression, we have big R. And that has a very special meaning. In SPSS, you will note that whenever you do linear regression, it always gives you the big R, even if it's simple or multiple. I want you to separate them in your brain. If it's simple, it's a small r. If it's multiple, it's a big R. And the reason for that is they are slightly distinct concepts, even though they purport to describe the same philosophy. So this is the multiple correlation coefficient, big R. Small r was just the correlation coefficient. Big R is the multiple correlation coefficient. If I run a multiple regression, I can extract from that final equation a big R. What it tells us is all these variables, when taken together, how well do they explain the dependent variable? So how well does attitude plus height explain the time in prison? The same way that how much does attitude alone explain your time in prison, which was small r? So big R indicates the magnitude of the relationship, but not the direction. Remember, in correlation, if you had a minus sign, that was a direction. It means that way. Big R, there is no minus sign ever. It goes from 0 to 1. It never goes negative. That's an important distinction between small r and big R. So you can never tell whether the direction is positive or negative just by looking at the multiple correlation coefficient. Okay? So we tend not to report big R. We always report big R squared. And that's called the coefficient of determination. A lot of terms, right? So one was the multiple correlation coefficient. You square it and you get the coefficient of determination. So remember, small r squared described the degree of variation explained by one variable in the other. This is kind of the same thing. It's the proportion of variance in the dependent variable, in other words, the time spent in prison, accounted for by all the predictors together. So if you're looking at how to predict your time in prison based upon your attitude score, your SES, your height, your race, etc., all that stuff together, if you square the big R squared, that tells us how all that stuff together, what percentage of the variance in how much time in prison that explains. So again, we want that number as high as possible. There's a couple of important aspects to big R. One is that it cannot be lower than the highest independent small r in the list. What does that mean? It means that, let's look at time in prison again. I can create a simple linear regression showing your time in prison, how much I can predict that based upon your attitude score, or your time in prison, how much I can predict that based upon your wealth, or your time in prison, how much I can predict that based upon your race. Okay? And each one of these will have a small r, a Pearson's correlation coefficient. When I combine them all into a multiple regression and I compute a big R, the smallest value for that big R has to be the biggest value of all the independent small r's. Can you see why that might be in lay language? Yes?
It wouldn't make sense if
Exactly right, because one assumes that as you're adding more variables, you're accounting for incrementally more of the variance. It's not logically possible to account for less of the variance. You're explaining more and more. So theoretically, if you knew everything about everything and everybody, you can predict everything about everything about everybody just by putting it into a big regression equation, right? So it goes back to what we talked about a couple of weeks ago when I showed a graph with a bunch of points. It's possible theoretically to plot a curve that goes through every single point by using a Fourier analysis or power series. I can get some really arcane, bizarre curve that goes through each one, but that's not useful. It doesn't allow us to predict things. So theoretically, I can, make a multiple regression based upon predict time in prison, attitude score, race, height, shoe size, how many siblings you've got, how much money you make, everything I could think about, and I can probably get a really high R squared, but that's not particularly useful because I got to be able to make predictions, right? So anyway, off on a tangent. He's absolutely right. We're adding incrementally more information, so you're explaining more and more. Okay. Now, second thing to consider about R is that, let's say I start out with predicting, again, how much time I'm going to spend in prison based upon attitude score. Okay, I compute an R. I get a number. I add on height. I get another R now. It jumps up. The R values went up. I add on race. The R value goes up again. I add on, the crime you committed. It goes up again. And interesting things happened. Each time it goes up, it's going up less and less. So I'm not getting big increments anymore. The more nuance I add to my equation, the less increase in accuracy I get. So it's a game of diminishing returns. I can spend all kinds of money and time and effort collecting more variables and more data, but I'm not gaining a whole lot more. That's why we tend to stop at a certain level. That's why we care about only modeling the best possible variables. Your hair color and what you have for breakfast that day, that's going to give me a little bit more, but it's not worth collecting. So that's an important research management nuance. So R, big R, is to multiple regression what small r was to linear regression, but it is not the Pearson correlation coefficient. Only small r is the Pearson correlation coefficient. We call it a multiple correlation coefficient, but it's not Pearson. Okay, so we could argue that small r is a special case of big R in the same way that simple linear regression is a special case of multiple regression. That's why I look at it. It seems to work for me. That's a confusing statement, so screw that. It's just that R squared is, that's not a useful statement. Sorry, it's probably more confusing than it's worthwhile. The point here is that R squared is what we care about at the end of the day. When we look at how good the fit is for a multiple regression, we go straight to the R squared, the capital R squared, and see how high that number is. Okay, that's a very high number, by the way. Usually in research, I see numbers like 0.2 or things like that. My grad student doing the woman in slums thing, her R squared is like 0.21, 0.24. That's acceptable because that's real life. Okay, the assumptions when doing multiple regression. Remember, we always have assumptions. First assumption is that there is normality again. So each variable that we're adding to our list of linear equations is normally distributed. So height's normally distributed, your attitude score, I don't know how to measure race, but let's say it is, those kinds of things. So also linearity. So each one of these variables, oh, that was my phone, that's not good. It's still on. Each one of these variables independently has a linear relationship. So attitude score and time in prison, that's a linear relationship. Attitude score and height, that's a linear relationship. Oh, sorry, time in prison and height, that's a linear relationship. So as I mentioned, each one in turn is linear. And this word here, homoscedasticity, remember that one? That means that all the variables in my soup there have more or less comparable variances, widths, splay, right? So how do you measure that? Well, Each one's going to be different. So the variance, each one's going to be different. But that one we tend not to look at a whole lot. It matters if, let's say, everyone has the same height in the prism that I'm collecting data from. That's got a 0 variance. That's not useful. So we want a splay that is useful. So some more assumptions. The errors are independent. What does that mean? It means that the reasons that once I predict your time in prison and I'm off by a little bit, and I predict your time in prison, I'm off by a little bit, it's not because you guys are in cahoots or that you're sentenced together at the same time. They're independent relationships. Okay, and almost knocked over again. Because I'm stepping on my cord. That's not good. Okay. Okay, so the residuals mean exactly the same thing in multiple regression as they do in simple regression. It's the difference between what you predicted and what you observed. We tend to plot the residuals to see what the splay is. That's one way of doing it. We always use software to do this. We never do it by hand. And if you want to look at it in SPSS, just go to Analyze, Regression, and Linear. It's right there. And that's the last of multiple regression. It was an ordeal, I know. We're almost done. The course is almost done. Any questions? Yeah? No? Right? Okay, cool. Oh, Friday I'm not here again. So, sorry. Friday I got to travel again. So Friday will once again be a class taught entirely by YouTube. I'll send you the link.